welcome to the last session of our drone workshop. My name is Milad, and today we will take a deep look into frequency analysis and vibrations of drones. And as you know, before we start to dive into the topic, I would just like to check if the audio is working fine for you. So for everyone who can hear me, please raise your hand using the raise hand function in GoToWebinar. That looks very great. In the case you have some problems with audio, for example, the quality is bad, etc. Again, for this webinar, you can use our toll-free dial-in service via phone, and then you're connected to the audio broadcast just using your phone. Great. So yes, first of all, nice to have you all here. I'm very happy that so many of you were active in the last weeks, and let's maybe before we really start to talk about vibrations, take a quick look at the agenda. So the last 4 weeks, we really discussed a lot of different aspects of drone design and how to use engineering simulation to optimize the drone. So the first session, we took a look at aerodynamics, and later on, yes, we were talking about structural design and structural tests. So we did a static structural simulation of a drone part as well as of assembly to understand or to find out about physical limitation or mechanical limitations regarding the structural strength. And last week we even did some kind of crash test, drop test for or with different simulation setups. And yes, today we'll talk about vibrations, and vibration is something we will take a little bit more about it later on, which are, let's say, a basic physical phenomena, which is used in different industries. And for drones, there are maybe two things or two aspects of vibration which can become very interesting. The first aspect is that a part, for example, can be a lot of let's mention a lot of aspects we could focus on, but today we will really focus on first of all the fundamentals, because here again it's very important to understand what actually the kind of simulation means, what are the and now it should work again. Great. So you can see now the agenda, yes, and first of all we will talk about the fundamental of mechanical vibrations. Then we will again do a simulation setup. Before that we'll talk about the last work, homework for sure. And then we will together interpret the result of the simulation. I will present the homework assignment to you as a final one we have, and then we'll have time for some question and answers. Yes, my name is Milad. I introduced myself 3 times in the past, so yes, let's try. I will try to keep it very crisp. Yes, I'm here working at SimScale as Academic Program Manager, so me and my colleagues are trying to make SimScale the one place in the world to learn and do engineering simulation. And yes, like the last times, this workshop is really about to show you the first hands-on steps for using engineering simulation in drone design or design in general. So we will really focus on how to use this analysis types and how to use the results to have a better design decision, for example. And therefore we cannot have a whole full training about the fundamentals of simulation theory with a lot of math and applied physics. So if you're interested in that, you should check out some good books or university lectures. And if you're interested in a really detailed training on the general practical application of simulation, then this of course is also not, let's say, the absolute right choice for you, because it's very specified and hand-on. But you can win a free professional training, as you know, in the value of €500 by submitting all your homeworks. So in the case you would be interested in a more general simulation training. And yes, we're doing this workshop because we would like to share our product SimScale with you. We would like to see you using SimScale, to share our know-how, and also, yes, for sure to get product feedback. And if you would to contribute something, for example, on simulation, it would also be something we would really appreciate. yes, last let's say introductional thing. Some quick facts. Just I mean, this is the last session, so we will today have again a 1 hour online session with a live demo. And maybe because some question were asked again and again, yes, this workshop will be recorded, and please really focus on this workshop or on this webinar. So you should not start simulating before this workshop is finished. Yes, you are all provided with free access to SimScale, so you can simulate yourself. And if you need support or help, please use our forum. And maybe just one general thing, because some of you wrote in the forum that they had issues with finishing the second level of the last homework. Therefore, we decided to extend the homework deadline. So the new deadline is tomorrow, 4 p.m. You have additional 24 hours time to finish your homework. And after the session, me and my colleagues will contact those of you who had this problem, especially the problems with storage, and find a solution so everybody will be able to submit this homework. Great, then again, thank you for all your submissions, all your work. And I would just like in 2 minutes discuss the homework of the last week. So let's start with homework number or level 1. And here I just put it the plots of the displacement of tip 2 for different against the time for different drop or fall velocities. And a little bit confusing here is maybe that the scale of all these diagrams is a little bit different. So, but what you can actually see is that for sure what makes sense, as higher the fall velocity is or the impact velocity, as higher the displacement of the tip. For example, here we have a maximum displacement for y direction of nearly all directions at 0.05 seconds. That is just the impact point, and at 0.09 meters, so what would be 9 centimeters. And here at 5 meters per second, it's even 0.13 meters, the maximum. And here it's even bigger. And this is not to say very, very interesting. What is more interesting, I think, is the second level, because in the end, the first level was just about to get introduced to the simulation setup, and level 2, we really use the full assembly with the contacts. And here you can see the maximum von Mises stress, which is, let's say, measured for every time step within the frame of the drone. And here you can see for 1 meter per second we have the maximum von Mises stress of 3.5 megapascal. At 2 meters per second it's 23 megapascal. For 5 meter per second it's 91. For 10 meter per second it's 122 megapascal. And now the good thing is, let's say the critical stress of ABS, of this elastic material which the drone chassis is made of, is about 45 megapascal. So till 45 megapascal, most of the deformation will be only elastic, and you can really see that for 1 and 2 meter, our design is fine. But if you have a higher landing speed, something between T2 and 5 meter per second, the stress will become too high, and you will go cracking in the chassis or some other failures of the material. Okay, are there any questions related to the last homework? Great, then let's start to discuss about the fundamentals of mechanical vibrations. And here we have three examples of your daily life where vibrations have a big impact. We're starting with the clock, you know, these old style clocks where you have this swinging arm, which is in the end used to change the time on the clock. Or you have this swing boat, which you will find on some adventure parks, or for example a guitar. And all these three things are based on mechanical vibrations. So when we look at the clock, for example, the time it needs until it's going from here to here and back at normal position, it should be exactly 1 second, because this is used as an input for the clock. The swing boat, it's also again it's about mechanical vibrations, and here we have the movement of this boat, which is attached with sails here, and in the end it's also a frequency or periodic effect. And for sure, if we have a guitar and we want to make a sound, then the swinging is responsible, or is then later on transferred into acoustic signals. And so if we talk about vibrations, there's some things you should just know which are important. And I think to understand why this is important, let's just make a very easy example. And then I think a lot of things will become more vivid and more easy to understand. So just imagine you would have a spring. So I will use again my sketching tool. And the spring is fixed here, so it can't move. And then we have a weight. And now, for example, we would like what happen if I push down the weight, what will happen with this whole system, what will happen especially to the spring. And since it's a spring, I think you all can imagine what will happen. It will start to shake. So in the end, if we would put a tracking point, for example, track this point, it would be something like this, and becoming flatter and flatter until it stopped to move. And what happens here, you can even analytically calculate it. This is, for example, a second year's, or could be an exercise of a second year mechanical engineering student. The problem right now is we can do it for such easy geometries, because just in the case you're interested, we know that if we would put a cut here, then you would know you have two forces, the force of the weight and of the spring, and then you can calculate a general equation which can exactly say for which weight and which stiffness how this graph will look like. But we can't do this for complex real-world geometries like a drone. And here again we have to use simulation to understand what happens. And here are maybe just one general thing why we're doing such simulations. I mean, for such a simple system we would not really need it, but just imagine you have a lot of parts or products which are somehow interacting with vibrations. For just very easy example are bridges, for example. You may all know this video where a troop is walking over a bridge with a wrong, let's say, a melody, and then the bridge just crashes because of the vibration which fits to the eigenfrequency, so-called eigenfrequency of the bridge. And the same effect can happen to drones or to car engine parts, for example. There we use this kind of simulation. And there are, let's say, two stages if you want to do a vibration analysis using engineering simulation. You need to do basically two simulations. The first simulation you need is a so-called frequency analysis, and this analysis is, let's say, without real boundary. You would not have to put it's independent. Let's say it's better, independent from a lot of other boundary conditions. For example, the frequency analysis does not care about which load is acting on the part. or stuff like that. It's just important what is the geometry and what are the materials and the context between these materials. And what this frequency analysis will return us back is, in the end, it will calculate for which frequencies we will have, or we will reach eigenmodes of the part. So eigenmodes is, let's say, eigenmode is, you have then an eigenmode when you are applying a frequency with on a part which is similar or equal to the frequency of this part, of this eigenfrequency of this part. So this is the natural frequency of the geometry of the part. And so if you reach this frequency, you will have some effects. So it becomes stronger and stronger. And what this frequency analysis in the end is doing, it's just for us calculating for which frequencies we have a eigenmode. So the result will look like this. And then later on, we also know the operating mode. So in which range of vibrations will we operate? This can be, for example, the RPM of the engine, because every engine also creates small vibrations. And what you would do then is to only investigate the areas around the eigenfrequencies which are lying into your, let's say, to the band of your frequency using. So if we have here, for example, in this area, the operating mode, then we would only take a look, let's say, here and here. And we get really back frequencies from the simulation, to which we then use later on as the input for the harmonic analysis, which is really calculating the reaction of the product of the assembly through the application of the oscillation. So here, frequency analysis is only calculating on which frequencies something will happen, and then with the harmonic analysis, we're calculating what will happen at these frequencies. Great. Then we can even start with our first simulation about vibrations, and I will right now show you how to set up this frequency analysis, this first part. And this will also be, to do this again, will be your homework. For sure, we will again provide step-by-step tutorials. And level 2 of the homework, which I will present later on more in detail, will be then about using the results of this first simulation to set up the harmonic analyzers. And again, we will start with uploading the CAD model of the drone. Then we will create a mesh, define the simulation setup, and then take a look at the results. Okay, and this is, yes, our CAD model, or what we want to simulate. So that's again the drone, and in this case we have a little bit modified the geometry, simplified it, but it's quite similar to the one you used last time for level 2. So we have different solids for the engine, for the arm, for the two screws, and for the battery. And we will now just calculate the eigenfrequencies and eigenmodes of this assembly. And yes, first of all, we have to start with a CAD upload. So I will create a new project. Give it a name. And then I can upload the CAD model I want to use. I will just specify the file format step. And then I can take it from here. And after several seconds, or for bigger geometries, it can also be a minute or two, your geometry is updated or uploaded to SimScale, and you can now access it on SimScale on 3D. Here again, you can check if the scale is right and the number of solids. This all looks fine. So we can directly start to create our mesh. And again, we will use the AutoCAD mesher with custom refinements. So first of all, let's give a nice name to our mesh project. I will just call it mesh. Then we have to choose on which geometry our mesh should base. So in this case on drone. So the geometry is uploaded. And then we have to add a mesh operation. And here choose tetralization with refinements. And in the first step, then we have just defined the base mesh size, let's say. So the standard mesh size of the parts, if there will be no other refinement. And here we'll have now a maximum of 2 millimeters and a minimum size of 0.8 millimeters. We'll use again a first order mesh. Choose cos as a net gen 3D fineness parameter and use 8 cos to accelerate. So the time we just needed to mesh the geometry. And here again we have prepared the and in contrast to some other tutorials in the past, we will provide you here with some pre-prepared refinement zone. So the next thing you would have to do is to create a mesh refine, because here are some parts which we have to refine. Otherwise, it will be too cost for the simulation. And here we will use, instead of just selecting the faces, we will again use ready-to-use entity types. So where we have already grouped surfaces, because that will save you a lot of time for creating the so-called refinement zones. Okay, then I think this is clear. There should be no. Oh, there's a question. Just 1 second. I think it's related. Yes, there's a question by Mahmoud, and he wants to know if eigenmode and eigenvalues have something in common. Yes, they have. And this is really a little bit nerdy, but let me explain it. It basically comes both from linear algebra, and Eigen was yes, a guy, a mathematician. It was not. It was started by a mathematic Hilbert, to call it Eigen. And in the end, eigenvalue, you know it from a matrix, for example. And the eigenmode is, if you would take a look at the mechanical problem, how it would be a special steady state of this wave. So that's why it's called eigenmode. I hoped that this answered your question. And if not, I will for sure try to answer it again later on. Great. Then yes, let's go back and work on our mesh. So let's now start to create this mesh refinement. And by the way, if you click on topological entity sets in this tree, you can see the 3 sets we've prepared. And if you want to see which face we are really talking about, let's show you a quick trick. We will hide everything, we'll select all, hide everything, and now just show here the faces. So here you can see the faces where we'll add this refinement, and it's mainly in regions where we have contact later on. Okay, now we can add our mesh refinement. So we will call it high stress zone refinement. And define maximum minimum edge length. change the finance parameter to 3, so moderate. And now we can change the selection to face sets. Just select the 3 face sets, and our refinement zone is assigned. And now our mesh is ready for computation, so we just have to click here on the meshing operation in the project tree and click the start button. Now on the next, let's say 5 minutes, our mesh will be created or computed, and we can access it in the web browser. So yes, so let's do a quick summary what I showed you right now. Again, how to upload a CAD model as a step file. We created a TAD mesh with manual refinement, and what will be advanced, we would talk about CAD cleaning, preparation, and mesh quality assessment. So all the geometries we provide you, we are providing you with are, let's say, clean and ready for simulation. If you're using your own designs, it can be sometimes necessary to simplify the model or to merge different volumes. This is something where you can find more information on our documentation, for example. Now the mesh is going to be calculated, and that is quite good because now we can start with the simulation setup. And for sure I've prepared a project with a ready mesh. So when the meshing is done, the mesh will look like this. We can then switch to the simulation design and create the simulation. So new simulation. Now we have to choose the kind of simulation we want to do, and we will use a frequency analysis save. And then first of all we have to create the mesh, choose the mesh we want to use for the simulation. Here in this middle color drop-down menu. And first thing we will do this time is we will create so-called topological entity sets. That is the same what we just used before for adding the refinements. And it's now based not on the geometry, but on the CAD geometry, but on the mesh. And we will create this entity sets in order to have save more time later on, because then we can use them again and again. And creating these entity sets would take some time, so I will just show it to you. I've already prepared them for one part, and then the rest will be written more exact in the step-by-step instructions. So let me, for example, just first of all show you one of these topological entity sets. One of them is, for example, this one, or another one is this one. And here you can really see in the end what they're used for. We have grouped all surfaces. One was missing. Here, for example, which is symmetric to the z-plane. And then we can later on use it for the boundary conditions. Or for example, here we have defined two entity sets for contact zones, and we can directly assign master and slave without choosing them graphically or going through a list. And if you want to create such an entity set, let me just delete the symmetry, for example, here. You have just to pick the faces using your mouse. And now you can call it, for example, xsim. And now these faces were added to your to a new entity set. And if you, for example, have, like here, an entity set where something is missing, you unfortunately cannot edit these entity sets right now, but there's a trick. Then you just have to make sure to clear selections, then you select the entity set where you want to add something, delete it, and it will keep the faces will keep selected. Then you can select the faces which are missing and create it again. Yes, and we have another contact another phase for the lift force, for example. And in this case, the lift force was put here. But what for sure makes more sense is to apply the lift force, for example, on the propeller. But by the way, this is not important for this first simulation, so we can even just delete it. Yes. Next we have to define a contact based on this topologic energy sets. So, like last time, create a new contact. We can just call it contact drone, and now just to select this, choose contact zones, 1 for master and 2 for slaves, and our contact is defined. And then there is not so much missing anymore. For sure, we have to first of all define our model we want to use. So we want to work with gravity, yes. And in -1 direction, so to remove the minus here. Now we added gravity, and next of all we have to add the different materials that we want to use. So let's start maybe with the ABS, which we are using, for example, or which is used for the whole arms and base plates. And yes, there we have a linear, so standing the behavior of the material, don't have to change it, it's say standard behavior. And the only thing we have to adapt right now is the Young's module, and this is this. And the Poisson's ratio was a 0.35. And for sure the density. And we have to apply it, and we will apply it graphically to the chassis and to the propeller. Next material we need is the battery. And here it's in the same like for the ABS, you have only to adapt the Young's module, the Poisson's ratio, and the density. So .34. The density is 2500, and here we will add it only to the battery. And the last material which is missing is steel, and here we will use again our material library and assign it to the missing parts. So we have now assign it to this, the propeller, and for sure what is missing is the engine itself. But for the engine we could in this case, or we will in this case again, use a kind of custom material. Or we can also, if we want to simplify in the first step, just use again steel, because for a harmonic analysis the difference will not be so big. So let's just select the missing part here. Here. Great. Okay, now only things which are missing are the so-called boundary condition. Here we just need symmetry boundary conditions. So we will have a symmetry for the xy plane, and in the xy plane, x and y are constrained. We will add it to symmetry z, and we will add a symmetry to the yz plane, where y and z as a placement are unconstrained, and where we will use yes. Now we have no preload in this case, and yes, the only thing which is missing right now is to adapt simulation control with ace cause, investigate 10 eigenfrequencies, so you can just use the rest of standard values, and create a new run, start it, and your simulation will be executed on our cloud hardware, and you will get notified as soon as the simulation is ready to use or it's finished. Great, then let's make a short wrap up. So we talked about the general simulation setup of frequency analysis, how to create and manage topological entities, remember the trick how to modify them, and we again showed you how to define a material. We assigned the two symmetry boundary conditions and started the simulation. Oh. Sorry guys, I just made a quick I made a mistake with this boundary conditions. So it was the wrong way, sorry. It has to be exactly the other way. So let me correct my mistake. For sure, if we have your symmetry here, it can only move. Okay, now it should work. Great. Sorry for this. So next step is result interpretation, and therefore we will switch to the project which I've already prepared here, and then we can access simulation results. And here we will not use so much graphical post-processing. We will access two things which you can find in the post-processor. First of all, the eigenfrequency plot. So this one shows the different eigenmodes, so they're numbered 1, 2, 3, and which frequency they have. So we have at 0.009 eigenmode as well as at 393. And you can also have a table here, and you can also visualize the eigenmodes. For example, here we can change the field to displacement, and then we can check different eigenmodes. For example, here you can see the displacement. Yes, that's it. So we talked about eigenfrequency plot table and eigenmodes. And if we now want to make some result interpretation, we should really take a good look here to the eigenmodes, because what you can see is that I have really a big range of eigenmodes, and here we only calculated the first 10. And you can see, for example, that they have the same distance, so it's periodically. And for example, here what we would do now is to investigate what is the operation frequencies we want to take a look at, or which is, for example, the most important frequency, and then we would use this, investigate for a harmonic analysis for this or several of these frequencies. Great. Now I'm very happy to present your homework assignment to you. And sorry again for the confusion with the simulation setup before. For sure, we will provide you again with a step-by-step tutorial, so there should be no doubts or questions when you're working on the simulation. And your homework assignment will again consist of 2 levels. The first level will be to create this frequency analysis based on the CAD model, so you have to create the mesh and the simulation like I did before. And on level 2, you will use this result to create a harmonic analysis, and there you will then investigate difficult reactions if you modify the frequency and the material property of the ABS. So there you will do, in the end, 1 simulations with 6 runs, and you can use the same mesh which you've created for level 1. And I would even recommend this to you. Otherwise, you have to set up again the mesh and the topological entity sets. Great. Are there any questions which you have and or you would like to talk about right now? Okay, let me just collect these questions all, and then we can talk about them. Okay, seems that there are no questions today. Oh, okay. First a question by Alex. Hi Milad, is it possible to work simultaneously with 2 different data assignments? For example, one simulation running and another one entering new data? Yes, it's basically possible. So if I got your question right, you want to work on one simulation, let's say flow simulation, and you have a mesh prepared and the setup prepared, and you will now want to set up the second simulation while the first one is running, right? And that's possible. So at the moment where you click on here, create a new run, then you are creating a new snapshot and you can edit the rest of your simulation. Great. Are there more questions? Yes, Oliver has a question, I think. Okay, and maybe to go back to Mahmoud's questions, if eigenmode and eigenvalues have something common, maybe to make it more clear, an eigenvalue is really the eigenfrequency of the part, and the eigenvector is the eigenmode. I hope that helps. And yes, also got a message by Oliver who corrected me, saying eigen is not a mathematical, it's more like a proper. Yes, and that's right. In German, for example, eigen would be really proper, the translation. Okay, great. Since there are no questions anymore, I would just like to announce 2 things. First of all, we got a lot of feedback from you guys asking if there could be additional session, maybe focusing on thermodynamics or on aerodynamics of a plane, and we are right now discussing it. So we will send something around if there is a decision, and so there will be maybe a additional session for sure, which is not coupled to your homework. So for qualifying for the training, etc., these 4 workshops or 4 sessions are enough. So stay tuned for maybe for the additional last session about drones. And we will also host in the next weeks a very great competition regarding to drones, and they will also get some feedback from us, email with details. And at this competition, you can really win great things. Okay, great. Then thank you again very much for all your time and your effort you put into participating in this workshop. As you know, we will tomorrow put online the step-by-step homework assignment, the tutorial, and the project links. And yes, I'm really looking to get a lot of feedback from you, a lot of new simulation. Please use the forum if you have questions. And yes, have a nice evening and a nice weekend. Bye.